On 19 August 1958, Thor Missile 129 was erected on Pad 17A at the Air Force Missile Test Center, Cape Canaveral, Florida, in preparation for the second launch in the Able-1 space probe program. At the same time, operations to recover parts of the first vehicle, Missile number 127, were underway several miles offshore from the Cape. Subsequent study of the recovered parts indicated the explosion in Missile 127 resulted from a random type failure of the turbopump number 5 bearing. Because a fix for this type of malfunction had been developed, it was decided to reschedule Missile 129 to the last of the 3 launches in order to permit the incorporation of appropriate modifications. The scheduled September launch was then moved back 1 month, and Thor Missile 130 was substituted as the first stage of the second Able-1 vehicle. It was erected on the launch pad on the 22nd of September. All stages of the second lunar probe vehicle were identical to those used in the first launch. The second stage was mated on 2 October, the third stage on the 8th of October. A flight readiness firing with the Thor first stage had been previously conducted on 1 October. The fourth stage payload package, officially named Pioneer, was identical to that of the first launch, except for the addition of an ion chamber for radiation tests. The ion chamber was fabricated and constructed by the Space Technology Laboratories following a design of Dr. Van Allen of the State University of Iowa. It is capable of measuring the broad range of radiation intensity from 10 to 1 million roentgens per hour. This new experiment replaced the low sensitivity unit of the magnetometer experiment in the telemetry frequencies. During the period between the first and second launches, modifications were also made in the Florida and Hawaiian microlock equipment to permit cine-wave ranging operations instead of trapezoidal ranging as previously planned. In Florida, the associated antennas were also raised from the ground and installed on the trailer roof to permit a better look angle during the immediate pre-launch period. The countdown for the second launch began on 10 October. 2 of the 5 hours of built-in holds were utilized in tracing a random short in the payload package, and 1 hour was consumed in resolving a first-stage structural problem. In the early hours of the morning of 11 October, final preparations and fueling were completed. The gantry was moved back, and the missile stood poised in the flood of searchlights. During the critical period of the terminal count, a 10-second hold was called because of a failure to activate an arming switch. At 3:42 a.m. Eastern Standard Time on October 11th, the second Able-1 vehicle was launched from Pad 17A. Although operation of the missile appeared normal, later analysis of tracking information and telemetry data indicated excessive thrust. It was about 4% higher than expected, and autopilot drift in the first stage burning period. These 2 factors resulted in a 2.5 to 3 degree lofting of the vehicle by the first stage. The second stage also was lofted about 2 degrees. The total lofting effect contributed to a second stage shutdown velocity that was 200 feet per second below normal. This was not due to a fault in the integrating accelerometer, which cuts off the second stage burning. Instead, because of first stage lofting, the initial velocity and attitude of the second stage was higher than programmed, and the apparent velocity, as measured by the integrating accelerometer, was higher than the vehicle's true velocity, thus causing an early shutdown. Studies of telemetry data secured during the flight indicate that after second stage engine cutoff, and before ignition of the third stage, a disturbance of an unknown nature occurred and caused an error in the third stage azimuth by approximately 15 degrees to the north. This severe change of attitude might have resulted from instability of the thrust of the third stage rocket during the separation. Telemetry data indicates a spin rate of approximately 120 RPM instead of the expected 140 RPM. Preliminary analysis showed the third stage provided a velocity gain of approximately 11,640 feet per second. By the time of third stage burnout, the altitude and attitude of the vehicle were about 6 degrees higher than nominal, and the velocity was from 400 to 600 feet per second below the expected value. Although this velocity deviation is a small percentage of the 35,000 feet per second required, a velocity loss of only 1% reduces the maximum attainable distance by 1/2. All 8 vernier rockets were fired to give maximum increase to velocity. However, within a couple of hours, it was evident the probe vehicle would not reach the vicinity of the moon. About 21.5 hours after liftoff, the 4th stage reached its apogee of approximately 62,000 nautical miles, more than 1/3 of the distance to the moon. During the flight of the vehicle, more than 100 hours of telemetry data were recorded on magnetic tape by the tracking stations in the United States, Manchester, England, Singapore, and Hawaii. The tracking data received were more than adequate, with the exception of high-altitude Doppler. Preliminary analysis of telemetry data connected with the various payload experiments revealed that the high-sensitivity micrometeorite channel recorded 8 hits during the first 10 hours, while only 1 hit was recorded by the low-sensitivity unit. Quick-look ion chamber information indicated a maximum recorded radiation level of 9.7 roentgens per hour at a distance of approximately 8,000 miles. This level dropped to 0.2 roentgens per hour at about 15,000 miles. Knowledge of this nature is of vital importance whenever it is desired to put man into space flights or orbits. Calculations made after it was known the payload would not reach the vicinity of the moon indicated that it might be placed in an orbit about the Earth by firing the retro rocket. The first opportunity to fire the rocket came 28 hours after launch, when the payload, which was now on its path back to Earth, passed high over the Cape Canaveral launch area. These attempts to fire the rocket from Florida were unsuccessful. Attempts were then made from the STL station in Hawaii, but these also failed, and after a flight of 43 hours and 28 minutes, the vehicle plunged back into Earth's atmosphere somewhere over the South Pacific near the coast of South America. Inability to fire the retro rocket can be attributed to malfunction of electronic equipment due to degraded battery performance at low temperatures. Although it is possible to obtain batteries which operate at much lower temperatures, the mercury cells employed in the payload are the most efficient type of battery available in terms of maximum life and minimum weight. Various paint patterns, foil wrappings, and reflectors had been designed to control interior temperatures of the payload package at an average of 70 plus or minus 20 degrees Fahrenheit. However, several unpredictable factors offset this and lowered the temperature to 36 degrees, the most important factor being the incorrect attitude of the payload package in relation to the sun, which resulted from the performance deviations in the other stages as described earlier. Nevertheless, the launch of the Able-1 vehicle earned a place in history as the first vehicle to pierce deep into outer space, traveling farther and faster than any other man-made object. Most important of all, it collected valuable scientific data that provided a new insight into the nature of our universe and changed man's thinking on space travel problems.